Hey everybody, I wanted to go ahead and give you guys a little bit of a rundown of quiz number one, which you did last weekend. I wanted to go ahead and provide you all with the right answers, so then you can kind of reflect on what you got on your quiz and learn from this whenever it comes to the final exam and everything like that. All right, so quiz number one. The first question reads, when using the protein purification software and purifying a protein, you are provided with information about the protein or enzyme's thermal stability and range in which that enzyme was functional. Please explain how an enzyme's thermal stability can be used in the purification process. Okay, so one of the ways that this was presented is you would see something like enzyme stable up to, let's say, 50 degrees Celsius. Now, what that allows you to do, both in the software and in practice, is if you know that your enzyme remains functional up to 50 degrees Celsius, if you heat that sample to, let's say, 49 degrees Celsius, is your enzyme still going to be functional? Yes, it will. If you heat it up to 50 degrees Celsius, is it still going to be functional? Yeah. If you heat it to 55 degrees Celsius, what's going to happen to that enzyme? Well, you've gone above the temperature in which it's stable, so you're going to begin destabilizing that enzyme, in which case you do not want to heat it up to 55 degrees Celsius. But what this means is there are other proteins, so let's say that we've got a mixture of protein X, Y, Z, and your enzyme. If you have this mixture of these four proteins and your enzyme is good up to 50 degrees Celsius, and let's say protein X, and these are all just variable placeholders, so let's say that this is up to 40 degrees Celsius, this is 90 degrees Celsius, and this is 45 degrees Celsius. If you heat this sample up to 50 degrees Celsius, what's going to happen to protein X? It's going to be destabilized. So you've effectively kind of killed it off. What's going to happen to protein Y? Well, that's stable up to 90 degrees Celsius. If you heat it to 50 degrees, it's going to be just fine. Protein Z, on the other hand, well, if you heat that to 50 degrees Celsius, that's hotter than its highest temperature of stability. And so basically what you've done here is you've eliminated or removed, maybe not removed, but you've basically killed off 50% of the proteins in that mixture. So what the enzyme's thermal stability allows you to do is basically eliminate proteins that are not functional at a particular temperature. Okay. Now, question number two. When developing a standard curve for a Bradford assay, what were the labels of your X and Y axis? Now, I think I was fairly generous on the awarding of credit here. What I was looking for was A595 for your y-axis, and then either protein amount or protein, and I'm just going to put this in brackets to indicate this, protein concentration. I noticed that a handful of people said, oh, well, micrograms of protein, and then for concentration, they'd say something like milligrams per milliliter. I didn't dock points or anything for either of those offerings, or I'm sorry, for not putting units or anything like that. But basically, those are the things that I was looking for. So my y-axis is going to be labeled A595, and my x-axis is going to be protein amount or protein concentration. Question number three. When attempting to purify lactate dehydrogenase by ion exchange chromatography, what did you use to elute that protein? Okay, so the most important part of this was we used NaCl. So we loaded our protein with a lysis buffer, and that basically had a negligible, that's the word I was looking for. I was going to say mitigatable, but I don't know if that's a word, but that's not really what I was going for. This has a negligible amount of NaCl. And so what we did was we had buffer plus LDH, lactate dehydrogenase, and we washed that over our column. And those the Q-Sephiros beads that were in here, we're going to bind to our LDH and basically adhere to that. That's kind of our ideal in our design. Now, when we wanted to elute proteins, what we did was we used the same lysis buffer, but we included NaCl at a concentration of 0.2 molar, 0.4 molar, and 0.6 molar. So we did those 3 different concentrations. Every group did 1 concentration, but the point here that I wanted to drive at was the NaCl, because that NaCl is going to disrupt any sort of hydrostatic interactions between the LDH and that resin there. All right, question number 4. When attempting to purify lactate dehydrogenase by ion exchange chromatography, what wavelength did you use to check for protein presence? Well, this one, we started out with A280. And that was just our kind of general survey of, do we actually have protein in the sample? This A280, what this allows us to do is see that, yes, indeed, there are, well, specifically what we're looking for are aromatic amino acids, tryptophan, tyrosine, and phenylalanine, F. W, yeah. Okay, so those were the amino acids that we were kind of looking for. And those amino acids are obviously building blocks of protein. So if we have absorbance at 280 nanometers, well, then we've got what we're looking for. Or we do have protein in that sample. Okay, question number 5. I didn't want to sacrifice the resolution of this image and include the text, but basically what this question was here's a chromatogram. Explain the lines. What are those different lines? Well, this is exactly what was on your quiz, and I don't really have any problem with this. Okay, so what I mean is I don't have any problem showing, you know, the information that's here on this y-axis and here on this y-axis. Okay, but I'm going to dig into those a little bit deeper. So this blue line tells you that, yes, indeed, there is protein present. So in this fraction number 20, looking at my y-axis, number 20, yes, there's protein there. Okay, so then fraction number, let's see, let's go with like 45 or so. There's also protein there. 60 and everything between 45 and 60. There's indeed protein there because we have this really giant blue peak. There's a couple of other blue peaks, but that's just telling us that there is protein in each one of those samples. It's not telling us that our enzyme is present, but instead it's just telling us, yes, indeed, there is protein present. Okay, the next line that I want to talk about is the next line that I kind of see, and that is this pink line. Well, that pink line, one thing that you'll notice is that it gradually increases. So it starts down here, and it ends up here. So the pink line tells us, where our, in this case, for this purification, this was the addition of NaCl. And this is indicative of what's known as a gradient elution. The concentration of NaCl, starting at about fraction number, let's call that number 33 or so, all the way up to number 125, increased gradually. Now, what does that tell you and how is that useful? Well, if you're trying to purify this protein right here, I would say that the concentration of NaCl necessary to get that protein to elute, well, it's somewhere within this range right here. Now, I don't have hard numbers on this because the range of that gradient, I don't have that. You would obviously have this if you were doing something. So what we could say is that in fraction number 33, we had 0 millimolar NaCl. Then in fraction number 34, we had maybe 0.1 millimolar NaCl. And then we slowly but surely, every single passing fraction, we're increasing our sodium chloride concentration until we get to fraction, let's say 125 has a concentration of 1.5 molar NaCl. So we would be able to say, well, maybe about 0.4, and I'm not really drawing that scale very well, 0.4 millimolar NaCl will be enough to get this fraction right here, fraction, to elute. Okay, so that's helpful if we're trying to identify what concentration of NaCl we need to add to our elution buffer in order to get a particular protein to elute off of that. So that pink line tells us the range of our gradient for whatever agonist that we're adding to our elution buffer. Okay, now the last line is this pink line. I think I can erase a number of these things. Let's see, there's my erase tool. Okay, now that's better. Okay, it's getting kind of messy. And scene, there we go. Okay, so this last line is the red line. Now, we do have a label for that on this y-axis over here on the right-hand side of our screen, enzyme activity. So this is going to tell us basically where our highest enzyme activity is. And it shows us that around fraction number 80, we have our highest or our largest amount of enzyme activity. So what that tells you is the enzyme that we're trying to purify, well, chances are it's at about, well, fraction number 80. Do we have any of our enzyme in fraction number 90, 100, or 110 or anything like that? No, we don't. Do we have anything in 70 or prior? No, we don't. Okay, so now what you could say is, well, was this a good technique or a good method to purify our protein? And to answer that question, you would have to look at your chromatogram here. Okay, so would you be able to say that your fraction is, now let's, for the sake of simplicity, let's just say that there's 5 proteins. Yeah, 5 proteins in this mixture. Protein 1, 2, 3, 4, and 5. So we started out with 5 proteins in this mixture. Looking at this chromatogram and thinking about all of these fractions, and whenever I say fractions, I do mean like a test tube that holds 1 milliliter, and so the very first fraction, well, that's going to hold 1 milliliter right here. So 1 milliliter. Then the second fraction is going to be the second milliliter that comes off of the column, but it's also going to be a 1 milliliter fraction. Okay, would you be able to say that protein number 1 is limited to, you know, maybe 4 or 5 different fractions? Well, maybe 4 or 5 is a little bit too narrow, but yeah, protein number 1 is only going to be found in fractions number 15 to number 20. Do we have to worry about protein number 1 being found in fraction 110? No, we don't. So have we isolated from this starting material, have we isolated protein number 1? Yes, we have. Okay. Now, can you say the same thing for protein number 2? I think you can, kind of. You know, there's a little bit of a, like, you don't have great separation between proteins number 2 and protein number 3 because, well, this doesn't drop down and then shoot way back up. But, you know, do you have some level of separation between proteins number 2 and 3? I think that you do. Okay, now the important question, though, is have we isolated protein number 4 from proteins 1, 2, 3, and 5? I would say that yes, we have, because we have protein number 4, or our enzyme, that is limited to basically, I'm going to call that fraction number 72 or so to 87. So we don't have our enzyme isolated to a single fraction, but you could also look at this and say the highest amount or the largest amount of our enzyme is probably found at about fraction number 80. We don't have to worry about our enzyme being found in fraction number 110, 115, 120, and so on. So this arguably is reflective of a pretty good start to a purification. So that's kind of everything that we want to see here. The red line corresponds to enzyme activity. The pink line corresponds to concentration of whatever agonist you're adding to elute your protein. And the blue line corresponds to the presence of protein. They're just kind of general protein. All right. Well, I hope this was helpful, and I hope that in the future, if you have anything mixed up, this clarified some things. If you have any questions, please feel free to contact me, and I'd be glad to discuss this any further. Thanks.